Hello, um, welcome to a video where I'll be teaching myself or another mentor will be teaching you how to CAD in Onshape and CAD specifically FRC mechanisms. I'm Tal. I'm a mentor for ICRobotics. I graduated in 2021 and I've been mentoring since 2023, so around 2 years now. Um, in this first video, I'm going to go through how to make a master sketch, which determines the points of where our intake wheels are going to be, as well as our pivot. You can also include things like motor location, uh, though I don't think we'll do that for this one because we don't know much about the rest of the robot. So I don't know. We'll see. Um, I'll give you a quick example of what we'll actually be designing. Uh, We'll be making a slapdown intake, which means that it's driven by a motor or a pneumatic cylinder, but for this one we're going to be driving it with a motor. You can see in this one for example, you have your pivot point on this here, and that's where this whole intake arm pivots around. So it can come down. When it comes down, that's when the game piece is picked up, or we say intake. Maybe this is a nice GIF. Yeah, exactly like that, right? Picks up the game piece into the robot. Um, so the thing that we need to be concerned with an intake is one that like we leave it outside of the robot for uh, the smallest time possible, minimum time, because intakes they sit outside the robot, outside of the what we call the frame perimeter, or outside of the bumpers, which means that it's very easy for us to smash it into a wall or into this truss pole, for example, or another robot to smash into us, right? And if that happens, that puts our intake at risk. We could damage it, rendering it useless for the game for the rest of the game. In which case, we won't be able to operate our robot properly. Um, so it's pretty important that that intake works really well. It picks up game pieces quickly and it's able to retract and also extend very quickly, right? So you could see it before. This one came up and it came down, and it can come up very quickly too. I would think so. This one's probably a better example. Um, yeah, that retraction is sub half a second, which is great. Um, we'll be making an intake for the 2020 game. I just picked a random game. You can make an intake for any game. There's always a game piece that sits outside of the field that you need to pick up. Um, so in the 2020 game, you had to pick up these foam balls. They were effectively dodgeballs, and you had to shoot them into a goal. We won't be focusing on the shooting thing. We'll be focusing on the intake. So, like I said, so this is the game piece for the 2020 game. We called it a power cell. Um, Power cell is a yellow 7-inch diameter, medium bounce Dynaskin foam ball. Cool. One thing I will mention is every single year there's something called the game manual, this guy here, and it tells you everything you need to know about the game. It tells you, rules in the game that robots can and can't do, rules on how to construct a robot, dimensions of, the field. So it'll go through, this is this tall, whatever, and it'll tell you about the game piece. So that's what we're concerned about today. What we'll also be concerned about is the bumpers, and you'll see why later, as in the bumper construction rules. So I'll go back to the power cell. Okay, so it's a 7-inch ball. Cool. So now that we know that, we can go back to our sketch. We'll start a new sketch by clicking here, right? And I'm going to start on the right plane. After you've done that, you can click N to set your view normal to the plane. You can also click up here, but I just find N a bit nicer. After you've done that, we should drop our bumpers, right? So we're making a sketch of, partially the robot, the part of the robot that the intake is going to interact with, as well as how the intake is going to interact with the ball. And you'll see what I mean by that in a second. But anyway, we go to robot construction rules here, bumper rules. It in the game manual every single year, so it shouldn't be too hard to find. So the cross section of the bumpers looks like this. It's two pool noodles stacked up together with the plywood backing. So that's cool. What we'll do is draw that up now. This cross section, right? So it's always good to constrain things off planes or the origin because these will never ever move no matter what. Nobody can change them. You could go and come into the sketch and fat finger some like dimension or I don't know what, and then it changes your whole robot CAD and you don't know what changed and what went wrong. So we should always constrain things, and the best things to constrain to are the origin and the planes you see here, right? Additionally, because this is gonna be a master sketch, it's just gonna define the important points in our intake on a 2D plane. We're not planning on extruding this. So I'm going to make everything a construction line. You can do that by clicking on the line and then clicking up here, construction Q, right? Or you can click on the line and then click on the button Q on your keyboard. You can also, before you draw the line, you click Q and you draw the line, right? And it makes a construction line. But anyway, so that's going to be 2.5 pool noodles in diameter stacked up together. So I'll click D for dimension. You should always dimension things when you can, for the reason I said before. So that's 2.5 inch, and we've got two of them stacked up together, right? So that's going to be around that big. 2.5 inches. Okay, so we've got that. Then it comes back and hits a plywood backing, right? So we've got this one, and we've got this one, and construction line. These two, currently they're not in line, except they should be, like these 2 points. So I'm going to use the vertical constraint. That's this guy up here. You can also click V. And what the vertical constraint does, it constrains one or more lines or a set of points to be vertical. So when we click on points, it'll just make these two in line with each other vertically, right? So once I've done that, I can set the length of those. So they're going to be the diameter of the pool noodle, of a single pool noodle, plus the thickness of the plywood. So the diameter of a pool noodle is 2.5 inch, plus the thickness of a plywood, which is 3/4 inch, just like that. We probably also want to put in the radius of our bumper. So we can do that using a sketch fillet. It creates fillets or rounds by selecting 2 sketch entities or a point. So in this case, we can click on these points, or we can click on these 2, right? But I'll do a point, 1, 2, and we set the size using this R number. So it's a 2.5 diameter pool noodle, which means it's 2.5 inch divided by 2, because we're setting a radius. You can see here it's R 31.75 radius. The last thing that we'll do is you can still see that this can move vertically. We're going to pretend that this top plane is our floor, and we'll just say, we'll just say that. Okay, I got a bit interrupted there. I don't remember where I was at, but yeah, it can still move in the vertical direction. We're going to pretend that this top plane is our floor. So I'm going to dimension, the bottom of the bumpers to our floor. Can we do that? No. Worth a try. Yeah, like that. Okay. Let's say our bumpers are going to be, I don't know, 20 centimeters off the ground, so 20 mil. Yeah, keep in mind that all these units are in millimeters. That's what we tend to use when we design parts. Okay, cool. So we've drawn up our bumpers, and I guess, I don't know, the frame will kind of be like, I've just clicked on the rectangle function. The frame will kind of be like this, right? Actually, I'll make this a construction. Frame will kind of be like this. And frame is always going to be 50 mil because we buy 50 by 25 box tube, right? Cool. So now, what's next? We need to map the trajectory, how we want the ball, the game piece, to come up and into our robot, right? Because all of these rollers do something. They play a part in bringing the ball in. So we need to map how it's going to interact with the rollers. So the ball initially is going to be right up against the bumpers, right? Construction, needs to be 7 inches in width. It's going to be right up against the bumpers. Now, how do we get it to be right up against the bumpers? We can use the tangent function. So the tangent function, make a tangent relation between two sketch entities, or between a sketch entity and plane. Perfect. We're going to do both of those. We're going to make the ball tangent to our bumpers because it's going to hit our bumpers when it comes up. And we're also going to make it tangent to the floor because obviously it's going to be sitting on the floor before we pick it up. So that's the first state of our ball. Then it's going to move up and into our robot. So we need to draw another circle, keeping in mind that you're still using the construction lines. For this, I'm going to use a tangent constraint, an equal constraint, so that I don't have to use this dimension again. That way, if for some reason I want to change this number, I can just change one dimension and they'll both change. I'll demonstrate that. So the equal dimensions just go here. I click E to set it. Make those two equal, right? And now if I make this 8 inches, they both change in size. You want to have meaningful dimensions, so your dimensions need to have some kind of purpose and be easy to understand by, let's say, yourself who's looking at this kind of a week later and you don't remember what exactly you've done, or another person, for example. Yeah, and you want those dimensions to be meaningful because if you do that and you make a drastic change, it'll update the CAD correctly and it won't break anything. So the next point I wanted to sit at, I don't know, let's say over here, right? We'll make a tangent to the bumpers again. Keep in mind the bumpers are compressible, so you might not get the ball acting how you want when you come up, but this is something that when you prototype your intake, you discover, right? The next one is going to be sitting on top of our robot. Again, making equal to the original, because if I was to delete that, if I made those two equal, right, and I deleted the middle circle for whatever reason, that's going to lose its equal constraint. So we'll just dimension it to the original, future-proof it. Again, we'll make that tangent, right? So the ball is going to be moving something like this, right? Something like that. What I'll do is, we have to get rid of the blue lines. Pretty much what black means is fully defined. I can't drag it around, right? What blue means is it's not defined. I can still drag it around, but I want it to be set because this is going to determine the position of our rollers, of our intake rollers, right? You can constrain this as long as it's in the general area that you want. You can constrain this forever. I'm going to constrain this guy. I don't know. I'll constrain those two together, and I'll constrain this guy to this guy, right? So our ball is going to be moving up and into our robot just like that, right? So actually, I don't quite like how I've done that because now it's not too bad. Oh God. Okay. So our first roller will have to capture the ball, right? So, see, that's an issue, right? That the ball is going to get caught. So let's say around here. Keep in mind the ball is compressible, so we can still bring the roller inside of the ball in some sense, right? Something like that. That's going to be the position of our first roller. You can dimension this in multiple ways. You can dimension it based off like compression, as in like that. In this case, I'm just going to make it easy for editing later, and I'll dimension the position based off the planes that we know. Um, yeah. So what was that? 154.75. Well, we're always going to make that a nice round number, um, just so we don't have a lot of decimals everywhere. And it's still constrained in that direction. So again, I'm going to constrain off the origin. That's going to be 170, right? Cool. The next position I'll probably want is something like that, right? Again, construction line. Oh, I should dimension the diameter of this guy. So how do we know the diameter of our roller? In this case, because our intake is, our game piece is very compliant. It's a foam ball. I'm going to be using a hard roller. You know, there's two different types of rollers. You've got hard rollers and soft rollers, and compliant rollers. So this would be like a compliant roller. They're very grippy. They squish, but we tend to use them more for game pieces that aren't compliant. For example, this year in 2025, we had a game piece that it was just a PVC tube, like a cylinder. It was very hard, so it wasn't compliant at all, which implying that if you were going to build an intake, you were going to use something like a compliant wheel, like this one. But because we're not doing compliant mechanisms here, because we've got a compliant game piece here, um, we're going to be using something harder. So a nice thing that came up recently in the recent games is silicon tubing. Now this silicon tubing kind of like wraps around some harder material. You could use some thin aluminium, or you could use polycarb tube, or you could use carbon fiber. These kinds of things. So they come in all these different sizes, and they're supposed to be like stretched over. So I don't know how much you can trust this OD. We'll have to look into it, but we'll look at. You can see there's a lot of different options, so anything will work. Do they sell? No, they don't. Okay, no worries. Let's just pretend that we've got a 1.25-inch diameter roller, right? Like that. So you can see we still have to adjust that guy. So he just need to come down under 150. Sick. Again, make those two equal, and I guess we can make a third roller that sits up here and finishes driving it into the robot. Make these two guys equal. Make him a construction line. Cool. He needs dimensions on him. So does the other one that we drew before, actually. That can be 335. That one. Oh yeah, I don't like that. No, I don't know. That can sit there. You want to keep it somewhat organized for editing later. He needs something there. 275, right? There's not much compression there. We might bring that down to 272 maybe. Looking a bit better. Like I said, you need to prototype this and figure out how much compression is the correct amount. That can be ended off to exactly 100. Oh, I forgot something. These need to be distanced off each other because you can see, like in these intakes, let's say this one for example, each roller has a belt coming off it between the two. That's how they're driven. We're gonna have the same, and those belts come in. If I look at we use HTD belt, right? If we look at belts, they come in very specific sizes. You can see increment by 5. Sometimes you get these weird sizes, but mostly they increment by 5 teeth, implying that the center distances between our wheels need to be, somewhat set. They're not just whatever number we want them to be. So I'm going to get rid of these to give our rollers a bit of a degree of freedom, right? Put it around where I want, and then I'll dimension it off each other, right? Same for this one here. See? They can move in that direction. So what I'll do is I'll leave one of the dimensions. 175. No, not good. 170. Yeah, cool. Now I'll adjust these to be correct. So the way that we can do that is we go to this website, Recalc. This is a website that calculates how far your chain sprockets need to be, your belt sprockets. It tells you how fast your drive base will be if you give it, 4 motors, this reduction, and it weighs this much, that kind of stuff. It's a really nice website. Highly recommend using it. But for this, we're going to use the belt calculator. We're going to look at what we want. So we've got a target center of 142 millimeters, 0.2, right? Our teeth. So in terms of teeth, how do we know what we're going to use? Well, we can look at the standard sizes. Our intake might be hex driven, it might be driven by something else. What I mean by hex driven is we use a lot of hex shaped shaft. So I'll show you what I mean by that. HTD pulley, HTD timing pulley. You can see you've got a hex shaped hull, right? So if we go to the HTD timing pulleys, the smallest hex one is 15 tooth. That looks good, though we don't have much of those in the workshop, so we're just going to go straight to the 18 tooth, right? So yeah. So we've got an 18 tooth on this wheel here, to 18 tooth on the next wheel, and now it's given us all those different suggestions, right? We can see it's suggesting a belt with 70 teeth. It's got a 130 millimeter center distance. Not quite what we want because we want 142. See what the next suggestion is. 142.5 millimeters. That's perfect. So we'll change this to 142.5. And what I like to do, right, just so that we still have this page, it's a pretty nice page. You can see all these vendors, they sell, what do we want? 75 V belt guys. Whatever. It should be, I would hope that it would show 75 because it's close to what I asked for, but it doesn't matter. We can see WCP should sell a 75 tooth belt. Right, this guy here. It's back ordered, but I wouldn't worry about that. We can buy them locally. It's a bit more expensive, but we can buy them locally. Cool. So 75 tooth belt, that's correct. What I like to do is I like to copy the link, and that will just give you the link of all this data, and I'll go into the comments. I'll go mark up, draw an arrow to this dimension, tick, and I'll put in the recalculate link so that later I can come back to it if I want. I don't have to look back at what I did before. So we can do the same thing for this one. So we'll probably have the same number of teeth. You might want to run different rollers faster or slower. I don't know. Like I said, depends on what you've prototyped. But you can change the number of teeth here to include a ratio, right? Right now we just have a 1-to-1 between each between each roller. So for the next one, we want something that's closer to 107.357. So the closest one to that is probably that one. Yeah, it's 105. So we'll change this to 105. Oops, I'm not supposed to do that. 105. Perfect. Yep. So now that we've done that, we can do the same thing with recalc. I'll make a new comment. Markup. Point at this dimension. Sick. Right. Now we can figure out where our pivot point is going to be. So the way that we can do that, right, is we use the circular pattern tool. Because we've got a pivot point, everything is going to be rotating around a single point, which means that it's effectively going to be rotating in a circle. So the circular pattern tool, we can click on 1, 2, 3 rollers, right? We only need 2 of these. And you can see here, when we move the pivot point, this whole thing moves, right? So let's say we have the pivot point there. I don't know, whatever. We'll tick this now and we'll play with it, right? So we can adjust our pivot point. I'll constrain that off the origin again, because the origin is always the best thing to constrain off. Not always actually, but in this case it's not bad because nothing will break in the future. You can be guaranteed of that if you can turn off the origin. So yeah, what we're looking at here is when our intake retracts. Actually, this is not the best way to do it because we want to dimension, you know, where this front roller is going to be when the intake is retracted. Because essentially, when the intake is retracted, it needs to fit within the frame parameter, which is this line here, right? It's that line. So what we're going to do is we're going to dimension this to be, I don't know, 20 mil off. You might want more, just so we're not like, so the refs aren't suspicious that, you know, our robot is sitting outside of the frame parameter when we drive around. I mean our intake, but I'm just going to do 20 for now. And now we can play with this number, right? So depending on where we put our pivot point, it'll just go up like that. So that's cool. We can also change this angle, you know, bring it back a little more. If we rotate 90 degrees, that looks okay. Constrain off the origin. 170. So yeah, now we can see that's kind of the whole master sketch, right? When the intake is out, it's going to be sitting like this, and it's going to drive in the balls like that. You might actually have an issue there where the ball can't come in, right? Because it needs to go under this roller. The intake might need to like come up to let it in. Like I said, these are points that you'll find out when you prototype your intake. But essentially, we've got our rollers in position. The ball is going to come up this way. Once the ball is in, our intake is going to be retracted, and all the rollers are going to sit in these positions, right? Additionally, we've also figured out where our pivot point is going to be. So our pivot point, what we can do now is dimension. These are driven dimensions, so they're not actually going to be doing anything. But essentially, our pivot point is going to be 55.875 millimeters away from our bumper horizontally, and it's going to be 100 mil off of our frame. So then you can use that to position it. I guess actually you wouldn't, because you would have this sketch in your CAD later. But what was I saying? Yeah, you can kind of see where that pivot point is. And if you're not happy with how things are sitting, you can play with this. You can play with this angle, 110. So it sits a bit further back. Where's our pivot point? Now it's outside of our bumpers. So we would need to like move this, right? But now it's a bit high. You kind of want to keep your center of gravity low. So a high pivot point is not optimal. So we'll set that back to 90. Um, a nice thing, you kind of need to balance it because a nice thing about having it at a high angle is now your intake rollers don't take up as much space in your robot. You can see like if I set it to 90, they come out a bit further. But anyway, we'll bring that down there and dimension it like that, 150. So yeah, hope you learned something from that. In the next video, we'll be starting off our sketches for the ones that we extrude for the intake. And then after that, we'll be assembling it. So yeah, thanks for having a listen.